folks, how are you doing? So we have been talking about the dynamics of rigid bodies. We talked about the translational motion. We talked about rotational motion, rotation about a fixed axis, and we looked at a couple of examples. Now today, and in these series of videos, I'm going to look at general planar motion. We have a rigid body. It can have translation. It can have rotation, or it can have both. Now that's the case for today's class. If it has both translational and rotational motion, and of course the method we use to solve this type of problems, the method we use to analyze these type of motions can be used for just translational or just rotational motion. This is more general, right? Now in a planar motion, we have both translational and rotational motion, right? The rigid body goes through both translation and rotation when the whole motion happens. So as a result, we have to consider the effects of both linear and angular acceleration, right? When we are analyzing this motion, this type of motion, the general planar motion. So let me put it in to words. So in a planar motion, we have both translational, or better to say just translation. We have both translation and rotation. Let me put it this way. So the effect of both linear and angular acceleration should be taken into account. You get the point. Now, so how do I do that? Well, I pretty much put everything together, what we know from translational motion and what we know from rotational motion. Let me write it this way. For a general motion, let me fix this. For a general motion, we have, let me use a free body diagram here. Let's say this is my rigid body. It's a very ugly rigid body. Let me try it again. Not that it matters and it has a specific shape, but this is my rigid body, and it is under the effect of, let's say, a couple of forces, some random forces. I'll put some force here, F1, another force F2, another force F3, and etc. And it has some center of gravity. Let's put center of gravity somewhere there. I represent the center of gravity with G. Let me copy this and use it for my kinetic diagram. I actually don't need the, well, I guess I have to take it. I put it there, and then I can delete these since I'm looking at my kinetic diagram. Oops. Okay, so here is my kinetic diagram. This is center of gravity, and let's say this is some point in 2D plane, which means it's an axis in 3D space. The axis is coming out of the screen, and the equivalent of the axis somewhere there. Okay. Because of all these forces applied to my rigid body, it has some linear acceleration. Let's say linear acceleration, I'm going to put it on center of gravity. It has some linear acceleration. So that would be the mass of rigid body times acceleration of center of gravity. It's the vector. And it has some angular acceleration. Right? Let me see if I can make it a little better. Put it closer to where this is. And that would be I mass moment of inertia around center of gravity times angular acceleration. Now, what I can say is that for this type of motion, well, I'm going to get a set of equations, like 3 equations, but if you want to write them in vector base, or if you want to represent them as vector equations, 2 equations, because force force is a vector, right? Force and acceleration. So I'll write it this way: summation of all the forces applied to my rigid body is equal to mass, Newton's second law, times acceleration of the center of gravity. So this is pretty much the same thing as we had for translational motion. For the rotational part, I can say the summation of all the moments. Now I have to write it in more general term. Right? I want to write it since in this case the rotation, well, generally speaking, rotation cannot just happen around the center of gravity. It can happen anywhere, right? And I'm assuming in this case that the rotation is happening around point A. Right? The whole rigid body is rotating around point A. This case, the summation of all the moments applied to rigid body about summation of all those moments about point A can be written as multiplication of mass moment of inertia around center of gravity multiplied by angular acceleration plus mass of the rigid body multiplied by the acceleration of the center of gravity times d. And now this d is new, and that is nothing but the distance, we'll say the moment arm of mg. Right? We have mg here. This is a component of our on our kinetic diagram, and d is the distance, right? Shortest distance between the axis that the rotation is happening about it and the center of gravity. So I'm going to draw it, say, this way. Let's see if I can go straight. Let's say this is perpendicular. And this is D. Just for the sake of completeness, let me also put the vector from A to G right there and right there. This is just a vector connecting point A, which the rotation is happening around it, and center of gravity. Okay, so these are the equations, all the equations we need to analyze the general planar motion. Now this one, it's pretty much the same thing we had for rotation over the fixed axis. You see this term here, this extra term, it appears because we are considering the mass moment of inertia about center of gravity. Now, the equivalent of this equation, this is pretty much the same thing as summation of all the moments around point A is equal to, or net moment about point A is equal to IA, mass moment of inertia about point A, alpha. Fix that. Angular acceleration. Okay. Now, this term IA alpha includes both IG alpha, right, mass moment of inertia about center of gravity, and the moment caused by MAG. Right? it's pretty much this force. Well, it's not a force, but if you look at the kinetic diagram, mag multiplied by d creates a moment, right? You can think about it that way. So IA alpha includes both. So you can use any of these equations when you're dealing with a rigid body motion. You can either find the mass moment of inertia about center of gravity and find the acceleration of center of gravity, as long as you know the distance between center of gravity and the point that the rotation is happening about it. You're good to go. You can use this equation, or you can just find the mass moment of inertia about point A. And if you know mass moment of inertia about center of gravity, going from there to mass moment of inertia about point A is just using parallel axis theorem, if you remember that. So this equation is the same as this equation, and this term includes both of these two terms. So keep it in mind. We're going to go over a couple examples, but there is no difference between these two. Sometimes we prefer to use this one, sometimes it's easier to use the other one, but both of them are going to give you the same answer. Now let me just define these terms to make sure that we all know what we're talking about, right? A lot of these you have seen before, just to make sure that things are all, let me use a different color. So in these equations, summation of forces, well, let me define it this way, is the net force supposed to be net, applied to the body. Oops. Well, m is the mass of the rigid body. I'm not going to write it here, but ag, what is that? That is change this. That is absolute acceleration. The absolute acceleration of the center of mass. Let me write it this way. Absolute acceleration of the center of mass or center of gravity. Then we have net moment, summation of all the moments. That would be, I'll define that as net moment about A. About point A in 2-dimension, or it's better to say axis A, I guess, technically. It is an axis. IG, well, that we know is mass moment of inertia about the center of mass. Mass moment of inertia about the center of, let me see if I can write it down here so I can use that space. Center of mass. Then we have alpha. Well, again, these are not new terms. I'm just putting everything together just as a review and make sure that everybody knows what we are talking about when we're talking about these terms. Now, angular acceleration. This is angular acceleration. Let's say, just say of rigid body. Rigid body. Then we'll have D. I'll define D, as I mentioned before, is the distance, the shortest distance between the axis of rotation, or point A, and the vector MAG. MAG is a vector, since A is a vector, AG is a vector. So let me write it this way. Be more technical. So say moment oops, moment arm of MAG, let me represent the vector, MAG vector let's just add about A, right? Because that's the distance. The last term, well, IA is the mass moment of inertia about A. Mass moment of inertia about A. There you go. So that's all you need. When you're analyzing the motion of a rigid body, make sure you write the equation from Newton's second law. Summation of all the forces is equal to MAG, and this one is a vector equation, so it gives you two equations, and you have to write the equation for the moments. For moments, either about center of gravity or about point. Well, you write the moments about whatever is the axis of rotation. If you can find the mass moment of inertia about that axis of rotation, well, you can just use this equation, IA alpha. Or if you have mass moment of inertia about center of gravity and you have AG, well, from before, right, because you need to find AG in most cases anyway, you can go with this version of the second equation. So we're going to have three equations. Now, let me just put everything together, just give you a general guideline about, let me put it under problem solving steps. How do we deal with problems? Problem solving steps. Well, we're going to start with finding AG because we need that. We know how to do it from kinematics. Let me write it here. Step one. Find the vector, find the vector AG. And we know how to do this. As I said, from kinematics, whatever you know from kinematics, put a frame somewhere, study the point that you're interested in, somehow find the value of AG, the absolute acceleration of center of gravity. Two, once you get that, now you can draw free body diagram and kinetic diagram. Right? So you can draw the L1 and 2 can be done. Well, they're separate, so we can draw the free body diagram first and then find vector G. Draw the free body diagram of the body with all the external forces and let's say couples, whatever torque or couple you have that's on your rigid body, apply to rigid body. Third step, well, once you have your free body diagram, well, you need your kinetic diagram. So draw the kinetic diagram with vector MAG, right? The acceleration that is applied to the center of gravity multiplied by mass. Let's see, let me just add it here. Acting on the center of mass and also, or you also have to and also include IG alpha. Right? Now this is for the case that you are using the first equation for moment, right? You need IG and MAG. If you are using the second one, sorry, if you are using this one, well, as long as you find what the mass moment of inertia around that point that you have the rotation about it, you are fine. This is nothing. This is not a new expression. This is exactly what we were using when we were studying the rotation over the fixed axis. Right? So that's not a new expression. It's just pretty much the same thing. As I said, general planar motion includes translation and rotation. So we take translation into account and we take rotation into account. Last step, once you have everything set up, what you do is that you just you write the equations, right? Derive, I would say 3 independent equations of motion. Equations of motion. Let's just add this from both diagrams. Right? You have free body diagram and kinetic diagram. Now, let me see. Sometimes, probably I'm not going to add it here, but sometimes, just sometimes you do this and you don't have enough equations. You find the vector AG, you draw the free body diagram, you draw the kinetic diagram, and you realize that the number of unknowns are more than the number of equations. So you have to look into the kinematic constraints. Sometimes you have a bunch of pulleys connected together, a pulley and a mass connected together, and because of those connections, there are some constraints on your system. So you are able to use those constraints to come up with a new equation, to be able to solve the whole system and be able to find whatever you're asked for, like acceleration or a specific support force or some kind of velocity or angular velocity. So keep that in mind, that sometimes when you follow these steps, you're going to end up lacking one equation, or you're going to end up having more unknowns than number of equations you have. So you have to look into the kinematics of the system and try to come up with the kinematic constraints and some relationship between AG, acceleration of center of gravity, alpha, angular acceleration, or omega, even angular velocity. So sometimes you have to find a new relationship between these parameters to be able to solve for everything, for all the unknowns you have. Okay, I'm gonna now start looking into examples and see how can we follow these steps and find whatever we are asked when we are dealing with the whole analysis of rigid body dynamics.